Inside a massive high-voltage industrial substation, a multi-megawatt transformer sustains the electrical load of an entire manufacturing facility. The kinetic energy passing through these steel structures generates immense, continuous thermal stress. Industry standards dictate that facilities conduct an annual manual electrical inspection. A certified engineer arrives on site and utilizes a thermal imaging camera, measures the ground resistance, and logs the asset's operating temperature into a compliance report. This approach yields a single data point. It captures the operating state of the transformer at one specific hour on one specific day, assuming the asset behaves identically for the remaining 8,759 hours of the year. This timeline chart illustrates the reality between those inspections. A facility experiences sudden load fluctuations, a surge in production, or an intense ambient heat wave. The transformer's temperature spikes violently upward, sustaining damage that goes entirely unrecorded by the annual check. Relying on a single yearly snapshot to verify the health of mission-critical infrastructure creates a temporal blind spot. Within that unmonitored window, cumulative damage incubates unnoticed until the system fails. To understand exactly how these assets die in the dark, we can look at an empirical analysis of 536 real-world transformer failures. This visualization breaks down those 536 failure cases. The dominant cause of death is not structural or mechanical. It is the degradation of the winding and insulation. Prolonged exposure to high temperatures bakes the internal insulation. This continuous thermal stress creates microfractures in the insulating material, compromising its dielectric strength and rapidly accelerating the timeline to a short circuit. Protecting the asset requires moving away from time-based preventative maintenance. Instead, engineers must adopt condition-based predictive maintenance, relying on the Industrial Internet of Things, or IIoT, to monitor the equipment continuously. Executing this requires architecting a continuous, operational technology-grade IIoT data pipeline. It begins by extracting raw thermal metrics directly from the physical copper coils and securely transmitting them to a central dashboard for real-time analysis. This IIoT layer pyramid is the architectural model for predictive maintenance, starting at layer 0, the physical sensor level. Traditional monitoring measures top oil temperature, but oil heats slowly. For an accurate model, engineers embed a platinum PT100 sensor directly against the internal copper coils. By maintaining direct contact with the windings, the PT100 sensor bypasses the oil's thermal delay. It captures instantaneous, second-by-second thermal responses the moment the electrical load shifts. This line graph plots internal temperature against expected asset lifespan. As the temperature pushes past 90 degrees Celsius, the curves drop sharply. Even a sustained increase of a few degrees exponentially degrades the remaining life of the insulation. Without extracting this instantaneous thermal data at layer 0, calculating an accurate predictive assessment of the transformer's health is mathematically impossible. The raw data from the PT100 sensor travels to layer 1, the edge gateway. This device acts as a local aggregator, filtering and processing signals before they leave the facility. A common engineering error is attempting to use consumer-grade IoT microcontrollers in an industrial setting. Those boards are exposed and fragile. Industrial monitoring requires operational technology-grade hardware, shielded in protective casings and mounted securely to DIN rails. The environment inside a high-voltage substation is hostile. Consumer hardware fails instantly under the massive electromagnetic interference and severe temperature fluctuations. True OT hardware achieves industrial certification only after surviving rigorous environmental chamber testing, where it is subjected to continuous temperature and humidity cycling to simulate years of mechanical stress. The edge gateway is the survival link of the architecture. If this local processor cracks under industrial stress, the flow of telemetry stops, and the entire predictive data pipeline collapses. Layer 2 requires navigating a strict engineering trade-off, the balance between data bandwidth and transmission range. Wi-Fi and Bluetooth offer high bandwidth, but cannot penetrate industrial concrete. The solution is LPWAN, a low-power, wide-area network, sacrificing bandwidth to achieve massive geographic reach. However, deploying these networks introduces an invisible barrier. Engineers cannot simply broadcast on any frequency they choose. They must operate within strict national telecommunication regulations. Frequencies are legally restricted. For example, specific regulatory bodies mandate that industrial IoT hardware must operate strictly within narrow bands, like the 920 to 925 MHz spectrum, to prevent interference with public infrastructure. Architecting IIoT communication requires carefully balancing signal physics with bandwidth limits, all while maintaining strict compliance with regional broadcasting laws. Transmitting data over the air exposes systems to external threats, bringing us to Layer 3, cybersecurity. Securing an operational technology network requires a completely different paradigm than securing standard IT infrastructure. An IT data breach results in stolen records or financial loss. A breach in an OT network grants a malicious actor direct control over physical, kinetic machinery. Consider an IIoT system connected to an automated ecotap, a mechanical mechanism that automatically adjusts the voltage ratio of a transformer. It does this by altering the number of active coils. If a threat actor intercepts this connection, they can remotely manipulate the tap changer. Forcing an abrupt voltage misalignment at peak load physically overloads the grid, triggering a catastrophic fire and destroying the multi-million-dollar asset. Defending the physical asset requires enterprise-level cryptographic shielding and strict adherence to frameworks like ISO 27000. ISO 27000 is an international standard outlining best practices for managing information security, ensuring the OT network remains fully isolated from public internet vectors. In industrial IIoT, cybersecurity is a physical safety mechanism. It is the only thing preventing the weaponization of the power grid. We reach the top of the pyramid, Layer 4, the cloud dashboard. This dashboard is built using tools like Node-RED, a programming environment used to wire together hardware devices and online services. The entire investment in sensors, gateways, and cryptography exists solely to populate this screen. The interface acts as a digital twin of the physical transformer. It aggregates disparate variables, voltage anomalies, harmonic distortion, and the internal coil temperatures into a single continuous feed. The system processes these variables to generate a health index. A health index is a single numerical value calculated from real-time operational data, telling the facility manager exactly how much operational life the transformer has left based on its cumulative stress. The dashboard monitors the thermal curve against the health index. The moment the internal temperature crosses a pre-calculated mathematical threshold, the system automatically fires an alert to the engineering team days before insulation fails. By making the internal degradation of the transformer entirely visible, this continuous data pipeline effectively eliminates the temporal blind spot of the annual inspection. The predictive maintenance model extracts internal thermal data, pushing it through ruggedized edge gateways, transmitting it via regulated LPWAN frequencies, and securing it behind OT-grade cryptography. Industrial IoT demands a rigorous, multidisciplinary engineering standard. It requires precise expertise spanning high-voltage power systems, radio frequency telecommunications, and cyber-physical security. The stakes justify the complexity. Implementing this architecture extends the lifespan of multi-million-dollar industrial assets and ensures the uninterrupted stability of the broader electrical grid. By constructing this data pipeline, modern engineers stop reacting to catastrophic breakdowns. Instead, they manage, predict, and control the future of their infrastructure.